This is a continuation of Chapter 8, and now we are actually starting chemical reactions, which is kind of cool. So the reactions we're going to talk about are reactions that occur in aqueous solution, water as the solvent. And before we start, I want to remind you of a very important happening that I've mentioned before, and that is when you dissolve an ionic compound in water, that ionic compound dissociates into the individual cations and anions. I also want to remind you that the AQ symbol means dissolved in water. Okay, so even though most ionic compounds are soluble in water, you will learn there are some that are not. And so if they're not, for example, silver chloride is an example of an ionic compound that is not soluble in water, and you'll see that designated with the S, means solid. Okay, it's not in a dissolved aqueous state. We call solids that do not dissolve in water precipitates. So that'll just kind of help you navigate through this unit on chemical reactions if you're kind of remind you of all those. Now, one last thing is the definition of a solution. Okay, it's technically a homogeneous mixture. Okay, so homogeneous obviously meaning when you mix two or more things together, if you look at the mixture and it looks like one uniform thing, that is a solution. Alrighty, again, basic vocabulary. Mixture is made up of one or more solutes. That's what you're trying to dissolve, okay? And if you hear heavy breathing in the background, that is one of my dogs because we just played fetch. So, and then the solvent, of course. Now, trying to dissolve. How's that? All right. Okie doke. But one thing to keep in mind is when you think of a solution, you probably think of a solid dissolved in a liquid, like salt dissolved in water, because that is probably the most common solutions we deal with. But solutions, the solute and solvent, can be any state of matter. You can have a solution that's two gases. You can have a solution of gas dissolved in liquid. That's what carbonated sodas are. You can have a solution of two metals. That's what an alloy is, okay? So it's not always clear what the solute and the solvent are. So it's important to understand if it's unclear, the component that's present in a lesser amount is the solute. And the component that's present in the larger quantity is the solvent. So air, for example, is a solution of gases. So it wouldn't be clear, like, okay, what's serving as a solvent in air? Well, you just look for the largest quantity gas, and that happens to be nitrogen. So nitrogen would be considered the solvent in air, and all the other gases would be solutes. Alrighty. Again, this is just kind of a reminder. This unit is tying together a lot of what we have learned up to now. So I'm just kind of touching base and reminding you of key points. We have talked about like dissolves like, the little saying that helps us remember that polar solvents will dissolve polar solutes and nonpolar solvents will dissolve nonpolar solutes. So being able to determine the polarity of a compound or two or more compounds is important for predicting whether or not they're going to be soluble. One of the things that we will talk more about later in a different unit is the energetics of not only chemical reactions but physical processes like dissolving. But just to kind of point out to get you thinking, for something to dissolve in something else, like look at the diagram, the picture at the bottom. Let's say for ammonia, that's NH3. To dissolve in water, which it does very readily. And hopefully if you remember anything from the last unit, you can see that ammonia and water are both very polar. They're both capable of hydrogen bonding, so they have a very strong attraction to each other. But what happens when you dissolve anything in anything else is the attractions that exist within or from one molecule to another, like let's say ammonia, those attractions have to be severed if it's going to dissolve, because if it's going to dissolve, it has to interact with the water. Same thing with a solvent, okay? The attractions, the intermolecular forces that go on between water molecules have to be, to a large part, severed, again, so that water can interact with ammonia. And so now look at the new attractions that exist between ammonia and water molecules, okay? These new attractions between solute and solvent have to be stronger, more favorable energetically than the ones that were severed to make this solution. You may have to listen to that a couple times to understand it, but that's going to be really important to understand that type of energetic in any type of physical or chemical process. All right, and we've talked about solvation before. So for if anything that dissolves in anything else, well, in a liquid, the liquid, and most time we're going to be talking about water, of course, solvates simply means surrounds. So when you hear solvate, I want you to think of surround. So the water molecules will solvate or simply congregate around whatever it's dissolving, and the intermolecular forces will be set up in the most favorable way between the solute and the solvent. So you can tell that the solute here is an anion, right? Anions have negative charges, so they're going to be attracted to things that have a positive charge. Okay, now water, being a covalently bonded compound, has no full charges, but it has partial charges because it's polar. And so the oxygen we know is electronegative, has a partial negative charge, and the hydrogens, which are not very electronegative, have a partial positive charge. So notice in the solvation of an anion, the water molecules all orient themselves so that the partial positive hydrogen atoms are facing the negatively charged anion. And it's the opposite for solvation of a cation. In the solvation of a cation, the partial negative end of water, the oxygen molecule, is what is closest to or surrounds the cation. So be able to recognize and actually diagram solvation. This is just kind of it's just a cool picture, to be honest, okay? It shows the same thing. So again, if you have cations, the water molecules are going to orient themselves with the oxygen closer. If you have anions, they're going to orient with the hydrogen atoms closer. Now, a mistake some students make is they get so used to dissociating ionic compounds in water that dissolve in water that they forget that covalent compounds don't do that. Covalent compounds are made up of neutral atoms that are attracted to one another. There are no ions. So let's just take a typical covalently bonded substance. What if we had CH2Cl2, okay? Covalently bonded, no metals in there, right? No ions. So that's not going to dissolve in water. Hold on, let me change. Let me pick something that's going to dissolve in water. Let's take methanol. Okay. There we go. That's polar, can hydrogen bond. It's definitely going to dissolve in water, but when it does, nothing in that dissociates. All you end up with, CH3OH dissolved in water, right? Okay, so no ions or anything. That's in general true for covalently bonded compounds. There is one exception of a covalently bonded compound that dissociates when it dissolves in water, and that is acids, okay? So there are some acids that aren't covalent, but the ones we're going to be dealing with and the ones you're going to see in organic chemistry if you take it are covalently bonded. Let's take hydrochloric acid. Hopefully you have seen before that the definition of an acid is that it is something that donates a hydrogen ion, okay, and that happens to be a proton, right? You can prove it to yourself if you need to, but that's why they call them protons a lot, because a hydrogen ion missing its one electron is actually just a proton. So acids are substances that donate a proton, and so that's what happens in water. When you dissolve an acid in water, the acid donates its acidic hydrogen ion to water, and so you end up with what we call the hydronium ion, polyatomic ion. Okay, and then what's left over is the chloride ion. And so acids are an example of a covalently bonded compound that dissociates to form ions in water. Now, you will see the representation of an acid dissolving or dissociating in water two different ways. You'll see it not showing the water at all, right? That doesn't mean there's no water there. It means that it's just easier and quicker. So, and then sometimes you'll see it showing the participation of water. These two representations are considered by chemists to be equivalent. Okay, it is understood by chemists that there are no naked hydrogen ions, that hydrogen ions associate strongly with water molecules, and so how they exist at a molecular level is as a hydronium ion. Now, this dissociation reaction, okay, of hydrochloric acid in water, let's see if I can erase. Yeah, it's getting too messy. So, it's correctly described as dissociation of an acid in water, but it's also correct to call that an acid-base reaction, okay? So, to kind of refamiliarize yourself with the definition of a Bronsted-Lowry acid and a Bronsted-Lowry base, okay? A Bronsted-Lowry acid is something that donates a proton, hydrogen atom, and a Bronsted-Lowry base is a substance that accepts a proton. So if you go back to the dissociation of an acid and water, the Bronsted-Lowry acid is HCl, okay, because we know it donates a hydrogen ion. The Bronsted-Lowry base is water, because you can see here, water is what accepted the hydrogen ion. So be able to identify acids and bases if you see a reaction written out. Now, as I mentioned, this unit delves into chemical reactions in water. So the first one we're going to talk about are acid-base reactions in water. Then we will talk about precipitation or double replacement reactions, and then redox or oxidation reduction reactions. But we're going to talk about neutralization reactions first, acid-base reactions. So on the last slide, I showed you where HCl, hydrochloric acid, is serving as an acid and water was our base. You can also react an acid with a stronger base, such as sodium hydroxide. So you are probably aware that when you react a strong acid with a strong base, the products are a salt, which is kind of our nickname for ionic compound, and water. So that'll kind of help you remember, because you will be expected, if given reactants, first of all, recognize which of the reactants is an acid, which of the reactants is a base, and then what the products are. So what happens in an acid-base reaction? Well, one of the products is always water, and that water is formed from the hydrogen ion from the acid and hydroxide from the base, okay, H2O, and then what's left over is going to combine to give you your salt. So you definitely want to practice some of these. Here's one for practice. So keep in mind that on your next unit test, it's not only going to be acid-base reactions you need to be familiar with, it's going to be precipitation reactions and redox reactions. So first of all, you need to identify what type of reaction it is. So HBr is an acid. How do I know that? Well, the vast majority of the time, chemical formulas are going to start with a hydrogen atom, right? So And I know that this is a base because it has an OH. Now, we will learn that not all bases contain a hydroxide ion. A lot of them do, but remember the definition for Bronsted-Lowry base. It's simply that a substance is capable of accepting a hydrogen ion. So it doesn't necessarily have to have this hydroxide. So now you have to remember, what are the products of an acid-base reaction? Strong acid, strong base. Water is always one of them. So I would recommend writing water down first, okay? Now, some students are going to be very tempted to go, wait a minute, I have only one hydrogen ion and I have two hydroxides. Is this going to make something funky that looks like this? No, 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 no. Don't fall into that trap. Water, that's it, okay? The extra oxygen, hydrogen, whatever's there will shake out when you balance the reaction. And now the other reaction or the other product is going to be a salt, an ionic compound. So what's left in this case? We have our cation or the metal, barium. So now you need to be careful because ionic compounds, remember, you have to assign common charges and crisscross. So barium's going to be combining with bromide. And I know the charge of barium when it's an ion is +2 and bromide's -1. So this is going to ensure that I get the correct formula for barium bromide. Alrighty, so now you can balance the reaction. So metals first. Barium's my metal. They are already balanced. I'm going to save oxygen and hydrogen till last, right? So I'm going to do bromine next. So let's see. I have one bromine on the reactant side, but I have two on the product side. So I'm going to put a coefficient of 2 in front of HBr. Now I have to do oxygen and hydrogen, and I know to do hydrogen first. All right, so I have 2 hydrogen from the barium hydroxide, and I have 2 more hydrogen from HBr. So I have a total of 4 hydrogen on the reactant side. Now looking on the product side, I only have 2 hydrogens, so I can easily fix that by putting a 2 in front of the water molecule. And I think I'm balanced. Let's check oxygen. I've got 2 oxygen on the product side and 2 oxygen on the reactant side. I am balanced. So these chemical reactions can get complicated. What are the steps that we need to remember to do? Okay, think about it for a minute. One is predict products. Okay, so that's going to be for acid-base reaction, that's going to be water and a salt. Okay, for the salt, you're going to remember to crisscross charges. And then you are going to balance. Alrighty. Since the reactions that we're dealing with in aqueous solution are going to involve ions, we're only talking about acid-base now, but subsequent ones will too, precipitation reactions. So we have different types of chemical equations that we use to represent these reactions. What I have talked about so far are simply molecular equations, and that's when you don't show the individual ions, okay? So we know, for example, that sodium chloride, when it dissolves in water, we know that it doesn't exist as an intact ionic compound. We know that it exists as the individual cation and anion, right? But the molecular equation doesn't show that. Okay, molecular equation would just show it as NaCl, and chemists hopefully would know how it exists on a molecular level. But there's something that we call ionic equations, which chemists use to actually, they're more representative to what's actually happening on a molecular atomic level. So, for example, instead, HCl, it's an acid, dissociates in water. All of these are assumed to be in water. But we know that it doesn't exist as an intact HCl molecule, that instead it exists as the individual hydronium and chloride ions. Same thing with this base, sodium hydroxide, which is also an ionic compound, right? So when it dissolves in water, we're going to have the individual sodium cation and hydroxide anion. Okay, so this is a total ionic equation. Overall ionic or total ionic. It shows all of the ions. And then we're going to learn how to write what we call a net ionic. So if you look at the total ionic equation I have at the top of the page, there are some ions that are identical on both sides of the equation. Okay, for example, the chloride ion. Okay, so we call those spectators because they don't change from the reactant side to the product side. They're just there kind of watching what's going on. They're not participating. So to get the net ionic reaction, you're going to cross out all of the spectator ions on both sides. So in this case, it'd be the sodium ions and the chloride ions, and you're going to rewrite what's left over. So for the reaction between hydrochloric acid and sodium hydroxide, an acid and a base, the net ionic reaction, what's left, what actually reacts, is simply hydrogen ion plus hydroxide ion to give water. And so net ionic reactions are really useful because they tell the chemist or the reader exactly what's reacting, and all the other ones just kind of go along for the ride. Here is a practice problem. I'll give you a practice writing total ionic and net ionic. This is the same reaction we just wrote a molecular equation for, so I'm going to go ahead and fill in the products from what we did on the previous slide. Let's see, and then to balance this, we had to do that. Okay, so now to start by writing an ionic compound, a total ionic compound, you want to separate anything that ionizes in water. You want to separate it and show it as the individual ions. Okay, so what all ionizes? Okay, we have strong acids and strong bases. And we haven't really talked about which acids are strong and which ones are weak. So at this point, for this practice, I'm just going to tell you that HBr is a strong acid and that barium hydroxide is a strong base. So they're going to dissociate. All right, then I want to remind you that any covalent substances other than strong acids are not going to dissociate. Okay? And ionic compounds that dissolve, ionic compounds that dissolve will dissociate, as we've been taught before, right? So I want you to go ahead and assume this is soluble. Barium bromide happens to be a soluble ionic, as most of them are. So anything that's soluble ionic, I want you to dissociate. So let's go through what we would have here. Now pay attention to coefficients and to subscripts, okay, because you want it to balance at the end. So far I'm going to get 2 hydrogen ions and 2 bromide ions when the HBr dissociates. And then when barium hydroxide dissociates, I'm going to get 1 barium and 2 hydroxide. Now when you dissociate, you have got to show the individual ion charges. You don't have to do that when you have them together in an overall neutral compound. But when you separate them into their ions, you've got to show their charges. So I know not to separate water because it's covalently bonded. It's not an acid. And barium bromide is an ionic compound that I am going to ionize, separate. And I know barium has a common ion charge of +2. All right, there we go. I have everything. That's the total ionic equation. All right, so now to get to the net ionic equation, I want to cross out all spectator ions. Those are the ions that show up on the reactant and the product side unchanged. So let's see. I see that bromide is on both sides and barium is on both sides. That means that bromide and barium did not participate in any chemical change. So what I have left over is hydrogen ion reacts with hydroxide to give water. Now we're at the point, and this will happen, that the coefficients aren't in the simplest ratio. You can divide all the coefficients by 2, so I'm going to go ahead and just do that. So it is correct, more correct, if you end up with coefficients that can be simplified further, to go ahead and simplify them. The remainder of this lecture will be describing the differences between strong acids and weak acids. So a strong acid, and there are only 6 or 7. Some texts will tell you there are 7, but they're right in this list here, and you do need to memorize them because we treat them totally different than weak acids in chemical equations. So strong acid, by definition, is an acid that dissociates completely. In other words, however much you start of with the strong acid, it's going to 100% dissociate into the cation and the anion, and there will be none of the original intact acid left. So I love this pictorial here, right? So a strong acid, before it dissociates, right, when you can think of it as when you immediately put in water, for a split second, it'll exist as that intact molecule. But immediately it will dissociate, and notice there's none of the intact strong acid left. Okay, it immediately dissociates into the cation, or the hydrogen ion and the anion. That's a strong acid. A weak acid will still act as an acid. In other words, it is still a proton donor. It will still produce a hydrogen ion when dissolved in water. However, most of a weak acid is going to remain intact in the molecular form. So let's look at our pictorial to get, make sure you have an understanding here. So this is how you put the weak acid into water. It's okay. It's initially intact. What will happen right away is some of that weak acid will dissociate into the hydrogen ion and anion, but most of it, 95 to 99% of it or so typically will remain in the intact form. So that's gonna affect the distribution of product, but it's also going to affect how we represent a strong acid versus a weak acid in a chemical equation. Similar differentiation between strong bases and weak bases. Okay, so strong bases 100% dissociate into the ions. Weak bases and neutral nitrogen containing compounds such as ammonia are probably the most common type of weak base there is. Notice that ammonia-based materials and some other weak bases do not actually contain a hydroxide like you're used to seeing in a lot of the strong bases. So they don't contain a hydroxide, but they produce hydroxide when they're added to water. Okay. Remember the definition, the Bronsted-Lowry definition of a base. What is it? It is a hydrogen ion or proton acceptor. So it doesn't have to have a hydroxide, okay, as long as it accepts a proton. And you can see here that ammonia did accept a proton from water. So it is a base. So there are a limited number of strong bases. So this is another thing that you need to memorize. Okay, so there are 6 strong acids and 6 strong bases. How I used to remember the bases is notice that all of the group 1A, so lithium, sodium, potassium, all of those hydroxides are strong bases. They dissociate completely. And then the heavier group 2A hydroxides are also strong, okay? But the lighter group 2A hydroxides, like magnesium hydroxide, okay, is not a strong base. And it's debatable. Calcium hydroxide, some sources don't call it strong and others do. So I tend to stay away from that on my exam because it's kind of in a nebulous zone. So what do we do with this information? All right. If you have a strong acid or a strong base, and you're writing out the total ionic equation, or the net ionic equation, they separate into their ions, okay? So we know HCl is a strong acid, right? So if you were writing out, let me start with a molecular equation. So the molecular equation for hydrochloric acid in water is here. Now, if I were to write out the total ionic equation, since I know HCl is a strong acid, I would immediately separate, dissociate it, ionize it, okay? I can't separate H3O hydronium ion that's covalently bonded. I have to keep it together. All right, so in this case, our only spectator ion is the chloride ion. So on the other hand, though, if the acid you're using is weak, and so memorize those 6 or 7 strong acids, and every single other acid that's not in that group is a weak acid. So since the majority of a weak acid or weak base remain intact, that's what we show in a total ionic equation. Do not split apart, do not ionize weak acids and bases into their ions, because that's not how they predominantly exist in solution. So let's look at this example where we have a weak acid, acetic acid, and a strong base. Barium hydroxide is one of the strong bases. Look when we go to write the total ionic. We're going to keep the acid intact. We are going to separate the base because we know it's a strong base, right? So then what are our spectator ions? Again, and this is typical if you have either a weak acid or a weak base, you're only going to have typically one spectator ion, whereas if they're each strong, you typically have 2. Anyway, so there's our spectator ion. It's only barium. And our net ionic looks like this.